the first speaker of this session will be Johan Ervenius. I actually practiced that as well. He's a systems engineer at Arista Networks. He's been working there for 6 years with customers that build everything from global WANs and large-scale data centers to media solutions and campus networks. And his previous experience includes more than 10 years of designing and automating networks within the fiber-to-the-home industry. So guys, please join me in welcoming Johan to the stage.
Thanks. Okay. Hello. My name is Johan Ervenius. That's how you pronounce it. Working for Arista Networks, based here in Sweden. The first RFC for Ethernet VPN was published in May 2014, so almost 10 years ago. And during these 10 years, it has really grown in terms of supported use cases and has, to some extent, become a Swiss Army knife for VPN services in Ethernet networks. My purpose with this presentation is to give you an overview of EVPN, what has sort of happened during these 10 years, and also show you what is sort of coming in the future and what direction the industry is taking. But let's start with going back to the time before EVPN. I mean, there were already deployed VPN standards, so why was there a need for a new one? We start with layer 3 VPNs. We have RFC 2547 created by sort of internet giants Eric Rector and Eric Rosen and Jakob Rector, and it was a BGP-based control plane. You had a stack label to identify the VPN. Most vendors were in sync, all love and peace, right? Then multicast was added to the mix. We had the Rosen draft, which introduced PIM to build multi-point GRE tunnels, and suddenly you had IP as the forwarding plane. And then the next generation MVPN kind of reused the layer 3 VPN concept with, again, MPLS as the forwarding plane, MLDP, point-to-multipoint traffic engineering, etc. Today, there are close to 30 different combinations of protocols and functions that make up what is known as MVPN. Then we have the E-line service, a point-to-point VPN, so basically a virtual wire between two sort of logical interfaces in the network. No MAC learning, no routing, simply sort of a pipe to replace the black fiber concept. But of course, competing drafts done by the Compella brothers. You had the Martini draft, which used LDP as the signaling plane, later added BGP for order discovery. You had the Compella draft, which used BGP as the control plane, so similar to the layer 3 VPN concept. And then the ELAN service, a point-to-multipoint layer 2 VPNs. Again, multiple drafts using either LDP or BGP as the control plane. So needless to say, consensus between vendors were somewhat limited, and to fill the gaps in these different drafts, a lot of sort of vendor-specific implementations were done. And the end result was, of course, madness. And for those of you old enough to know who this is, that is madness, and that does not include me. I had no idea who this was. So, in the beginning of last decade, people started thinking about sort of doing something about this. I mean, knowing the challenges and understanding the requirements, what if we could start again? And the result of that effort was EVPN, or Ethernet VPN. So in 2012, work started on the first draft that later became RFC 7209, which is an informational RFC specifying the requirements of EVPN. And the target was, of course, to sort of address the challenges with the different VPN solutions out there. And over the last 10 years, a total of 19 RFCs has been published that has to do with EVPN. Not all of them are shown on the sort of timeline here. And there are close to 50 active drafts in this area, so there's still very much active development. And like with most standards, right, I mean, vendors implement support for these well ahead of when they actually become standards, and the same goes for the 49 active drafts. Many of those are already supported by multiple vendors. And the first use case that was targeted was layer 2 VPNs over MPLS. So the RFC 7432 kind of fulfilled the requirements specified in that first RFC. So what did we get with this RFC? Well, BGP was reused as a control plane. But instead of, what was introduced was a new address family to advertise MAC addresses and IP prefixes in the network. And the first data plane that was used was MPLS, but later sort of other data planes were added in later RFCs. So that doesn't sound that much different from sort of a VPLS service, right? Well, there are sort of significant differences. The layer 2 VPNs, also known as MAC VRFs in EVPN, are represented by something called Ethernet virtual instances at all sort of participating PE devices. You have local MAC learning at each site, similar as for VPLS or any LAN service, I guess. But instead of relying on flooding in the network to make the presence of a MAC address known, a BGP EVPN update is sent by PE to all the other PEs in the network, sort of advertising that location. Another big difference is the support for multi-homing, which was lacking from VPLS, which makes it possible for a CE to be connected to multiple redundant PEs. And this multi-homing in EVPN allows both for an all-active design, where all links between the CE and the PEs are active and being used, as well as an active standby setup with only one of those links being active. And EVPN multi-homing also allows for more than sort of 2 redundant PE devices, which differs from legacy multi-chassis lag solutions, where you typically can only have two redundant devices. Looking at a BGP EVPN update for a MAC advertisement, we see that the address family is 25, which represent the layer 2 VPN. So same as for VPLS. The new sub-address family is 70, representing EVPN. And this, as shown here, is as I said, is a MAC advertisement, right? Which is in EVPN lingo, that's a route type 2 update. And these route types is what EVPN uses to signal various data for different type of services. You have type 2, which is this MAC advertisement that I showed you. You have type 3, which is what PEs use to sort of advertise that they belong or that they participate in a specific VPN. And then you have type 1 and 4, that are used for signaling state in multi-homing scenarios. In 2015 or later in 2015, RFC 7623 was introduced, and this was for combining provider backbone bridging with EVPN to optimize scale and performance in PBB networks. And this is simply referred to as PBB EVPN. I'm not going to go into any sort of details on this one, but we can just now sort of note that a second data plane option for EVPN was added. In 2017, an E-line service was introduced. This was RFC 8214, or Virtual Private Wire Service support in Ethernet VPN. And this was to then sort of target the Martini and the Compella draft that I mentioned before, so the LDP and BGP-based SEV-to-wire services. And comparing this to the sort of point-to-multipoint layer 2 VPNs that I showed you before, VPWS only can have sort of 2 endpoints per VPN, so similar to an actual wire, right? You have no MAC learning taking place, neither locally nor across the network. The simply sort of what goes in on one side comes out of the other side. You can still have multi-homing though, so this is an enhancement to the previous standards. And this is signaled using route type 1, so the same route that is used for signaling certain sort of multi-homing scenarios. An enhancement to this is called flexible cross-connect, which is about sort of multiplexing multiple attachment circuits across multiple interfaces into one VPWS tunnel. That part is still a draft though, even if, again, multiple vendors already support that. In 2018, there was an RFC describing how the MEF E-tree service could be combined with the EVPN. But again, not going into any details of that one. Next, we have the RFC that has really come to push the deployment of EVPN. And so RFC 8365 is called Ethernet, or it describes sort of how EVPN can be used as a network virtualization overlay solution with tunnel encapsulations over IP, as opposed to before MPLS. So with this sort of third alternative data plane, it actually consists of 3 different tunnel encapsulations. You have VXLAN, you have network virtualization over GRE and MPLS over GRE. And the reason it has really come to push the deployment of EVPN is, of course, data centers. These data centers are typically built with equipment that is less specialized than what you have in service provider networks. So building VPNs over MPLS is not really an option because the hardware doesn't support it. So the protocol of choice has, of course, been VXLAN. We have the control plane is still BGPs. I mean, it behaves exactly like a service provider network, but instead of PE routers being sort of the endpoints, we're now talking about virtual tunnel endpoints, or VTEPs, being the source and destinations of VPNs. We also talk about having an EVPN VXLAN overlay on top of an IP underlay. So it's just different lingo, but basically the same thing as a service provider network. The target use case initially was the same as for MPLS, so layer 2 VPNs. But again, in data center lingo, you would probably say stretching a VLAN between different top-of-rack switches. Looking at an EVPN update, again, a Mac advertisement, it looks more or less exactly the same as it would in a service provider network. The only difference is there's going to be a BGP community saying that we're now using VXLAN as the overlay, and hence we have a virtual network identifier instead of an MPLS label to identify the VPN. So one way to tell if a technology is successful or not is the need for functions to make it scale better. And this is the case with EVPN, especially in the data center. I mean, EVPN VXLAN by itself scales much better than a pure layer 2 network, but even EVPN has its limits, right? So if your network grows bigger and bigger, it's going to come to a point where you need to split your EVPN domain into multiple domains. But if you still want it to behave like one big data center, you need some kind of an interconnect solution. So this RFC 9014 is for interconnect solution in Ethernet VPN networks. It's also called EVPN gateway functionality. So with this RFC, it introduces ways to span a VLAN across multiple EVPN domains over either an MPLS or an IP network. And in case of MPLS, you could either use EVPN layer 2 VPNs or any of the VPLS variants, or PBB for that matter. So this gateway functionality sort of supports the conversion and the stitching of the layer 2 VPNs across these different types of networks and technologies. There are also solutions for stitching layer 3 VPNs together, sort of in a layer 3 gateway function. That part is still a draft, though. But again, multiple vendors already support that as well. Every service typically needs some kind of a fault management or performance management function. So in 2021, there was an RFC published for operations and maintenance procedures in EVPN networks. Again, not going into any specific details on that one. The next big enhancement to EVPN was RFC 9136, which was the possibility to advertise layer 3 prefixes, in other words, layer 3 VPNs. And published more or less the same week or month was RFC 9135, which is integrated routing and bridging, which is sort of connected to that, which is about combining routing and switching on the same switch. And layer 3 VPNs for EVPN has really found its way into the data center, where basically subnets belonging to a VRF are advertised with a VNI belonging to that VRF. In service provider network, the deployment of EVPN layer 3 VPN has not been as significant. And I guess the reason for that is that, I mean, comparing this to the older sort of MPLS VPNs, layer 3 VPNs, the difference in capabilities are really not that big. Not as they are for layer 2 VPNs, where the difference is huge. This new RFC introduced a new route type 5, which is basically then an advertisement of an IP prefix, as opposed to a MAC address, which was route type 2. Otherwise, it's pretty much the same. The integrated routing and bridging concept introduced mechanisms for routing between subnets on a switch. In legacy data centers, you typically had a central point where you did your routing between subnets. Could be, for example, a firewall. So traffic had to go to and from that firewall, even if you had to do sort of routing between subnets on the same switch. So very non-optimal traffic paths. IRB is all about sort of making the traffic paths optimal, so you always take the shortest path between your source and destination. And IRB comes in two different sort of variants. You have asymmetric IRB, which means you basically deploy every VLAN at every switch, and then you first do a routing operation to the correct VLAN, and then you bridge to the destination VTEP. And symmetric IRB, where you introduce a layer 3 VPN or an IPVRF that takes care of the routing between different VTEPs in the network. And there are pros and cons with these different sort of approaches. In 2022, RFC 9251 introduced proxy functionality for IGMP and MLD. And the purpose was, of course, to optimize multicast services in EVPN networks. If we take a layer 3 leaf-spine data center, for example, that perhaps uses EVPN for unicast services, but not for multicast, there's really no way of knowing where you have IGMP receivers or MLD listeners. So a multicast packet would be sort of sent from the sourcing VTEP to every VTEP in the network, regardless if they have receivers or not. And on top of that, you would also use ingress replication at the source, meaning that every multicast packet would be sort of copied to the amount of VTEPs you have in the network. This would probably work fine for, I don't know, low bandwidth multicast services, but not so much for high bandwidth streams. So what this RFC introduced was a new route type 6, which is the possibility then for a PE or a VTEP to advertise the presence of an IGMP listener, or sorry, IGMP receiver or an MLD listener. So if there is an IGMP join coming in locally on a VTEP, that VTEP would then advertise that it has a receiver for that specific multicast group. So this allows the sourcing VTEP to then only send the multicast traffic to the VTEPs that actually has receivers. So a big benefit. You could still have ingress replication though. So still, if you had multiple VTEPs with receivers, you would still send multiple copies of that multicast packet across the network. To address the challenges with that ingress replication, there are multiple ways of doing this. One way is to introduce PIM in your underlay. And with route type 10, which is a new route type, a VTEP could then sort of map a VLAN or a VRF to an underlay multicast group. So this means that, that the sourcing VTEP would, instead of using unicast in the VXLAN header, which is sort of the default way, it would use a multicast address as the destination in the VXLAN header, which means that the encapsulated packet would actually use multicast to traverse the network, and hence only sort of traverse each link once and get replicated in the network where it needs to be replicated, exactly how multicast is supposed to work. So what does the future hold for EVPN? Well, it's very active in terms of development, right? As I said, it's close to 50 active drafts. I think it's actually more than 50 active drafts now. A couple of new ones has been added since I made these slides. And to tell what is sort of really hot at the moment is to look at what is being tested every year at the European Advanced Networking Test Center, or EANTC. So this is an effort that takes place in February timeframe every year. And EVPN has really been tested more or less every year since it was sort of first published in 2014. Other technologies that are tested are, for example, segment routing V6, SDN, time synchronization. And this is really a big difference compared to earlier technologies, right? Instead of having the customers figuring out what works between equipment from different vendors or not, it's now up to the vendors to actually do this interop themselves. So huge difference there. And looking at what is hot at these ENTC testings, it's definitely EVPN gateway functionality. So this has been tested all the way from at least 2016-17, and it's continued to be of great interest in both 23 and 24. And when you think about it, I mean, interop solutions is gateway functions is where interop is really most needed. It's probably the place in the network where vendors typically have equipment from different vendors. I mean, a data center from one vendor, an MPLS network in between, from another vendor, or maybe a third data center or a second data center from another vendor. So this gateway functionality is what is really being tested right now, and what is also being very much active, sort of developed, looking at the different drafts that's out there. So closing the loop on the presentation, what did we have before and what did we get? I mean, before we had these overly complex sort of solutions using different multiple signaling protocols, multiple different BGP address families, and all of them with sort of vendor-specific implementations to fill the gaps in the different drafts that we had. So what did we get? Well, we got simplification, a single BGP control plane for all your layer 2 and layer 3 services. And equally important is that EVPN works on top of multiple data planes. So no matter what data plane you're running today and what you're planning to migrate to in the future, EVPN will work. So I mean, migrating to EVPN today is really sort of making your network future-proof. And with that, I thank you for listening.
We have time for some questions. Are there any questions for Johan? Okay, then please join me in thanking Johan for his presentation. Thank you very much.